In this video, I'm going to introduce the concept of the derivative, which is extremely important to Calc 1 and makes up about half of the content in this topic. So the derivative is actually equal to the slope of the tangent line at a point. So if we were trying to find the derivative at x equals 3, for example, right here, that would be the same as the slope of the line which touches the curve at exactly one point, looking something like this. Now just to give you an idea of the tangent line, if we tried to find the tangent line at x equals 1, it would maybe look something like this. As you can see, it just brushes by the function at one point and one point only. So say the slope of this line is 1.5, that would be the derivative at x equals 3. And we would actually write this with the notation f prime of 3 equals 1.5. Of course, that's completely made up. But if that were the slope, that would be the derivative, which we denote by f prime and then parentheses. Other ways you may see this denoted are dy dx at x equals 3. That is also some way that people write the derivative. Now, in this video, we're going to actually learn how you can approximate the derivative using a secant line. Now, a secant line touches the curve at exactly 2 points, as opposed to a tangent line which only touches at 1. And a secant line will look something like this. And so you can see here that it kind of sandwiches this point in the middle. And by doing that, it hopefully gets pretty close to the slope of this tangent line. So we're going to practice this real quick and see what an approximation of this derivative at x equals 3 would be using a secant line. And so just using the basic slope formula of y2 minus y1 over x2 minus x1, we can go ahead and see that we're going to just pretend like this graph makes a little more sense and that x equals 4 is like right here. So bear with me on that. But x equals 4, y is approximately 5, as you can see there. So y2 is 5. y1, right here you can see that at x equals 2, y is 1. That means y1 equals 1. And then x2 minus x1, our x2 is 4, our x1 is 2. So we would have 4 minus 2 on the denominator. Simplifying this real quick, 5 minus 1 is 4, 4 minus 2 is 2, meaning our approximated derivative is 2. So just to clear up a little bit of room here, we could write that f prime of 2 is approximately 2. We can also approximate the derivative using a table. So we're going to try this problem, which asks us to estimate the instantaneous rate of change at x equals 2. Again, we're going to be using a secant line here and try to find the derivative at this middle point, x equals 2. So we're going to pick 2 points that sandwich it, which are x equals 1 and x equals 3. And before I start, I'm going to write out the slope formula real quick and then go ahead and plug in our values. So these are the 2 values that we're going to use for the secant line, and this is the point at which we're trying to find the derivative, or the instantaneous rate of change. So we can see here that y2 is 9, and then y1 is 1, so 9 minus 1. And then x2 is 3, and x1 is 1. So we've got 3 minus 1. And now if we simplify this, 9 minus 1 is 8, 3 minus 1 is 2. We can see that the approximation for the derivative at x equals 2 is 4. So again, just going to clear a little bit of room. We are actually going to write this with the other notation this time and say that dy dx at x equals 2 is approximately 4. It's also important to recognize that the derivative is a function in of itself. So what does this mean? Well, let's say we have the base function f of x equals x squared. Now, if we found the derivative at every individual point on this line, that would have a value. And we can actually graph these values to show the derivative of that function. Basically, there's a connection between these 2 graphs in the sense that each point on this graph on the right is the instantaneous rate of change to its corresponding point over here. So there are different ways to find this derivative function, such as through the limit definition or other rules like power rule. So check out my limit definition video or power rule video if you want to see those. But basically, you just need to realize that there's this connection. Another important thing towards introducing derivatives is the connection between differentiability, which I'll explain what that is, and continuity. Differentiability means that you can take the derivative of a function at a certain point, just like continuity means that the curve is continuous and smooth at a certain point. before I explain what marks differentiability or non-differentiability, you need to understand this circle here. So essentially, differentiability requires continuity. This circle essentially represents every known function. And so, in order to be differentiable, a function must also be continuous. However, just because a function is continuous doesn't mean it's differentiable, as seen by this space out here, which represents continuous functions, but not differentiable ones. And so now we're going to dive into the three main ways that a function won't be differentiable. The first of which is for the function to be not continuous at a point. So you can see here that in this red graph we have a jump discontinuity as well as a vertical asymptote discontinuity, which means that at these specific points the function is not differentiable. Now, in addition to discontinuity, if there's a sharp cusp on a graph, like you can see here, it's actually not differentiable at this point. So this would be not differentiable. And the reasoning for which it's actually not differentiable at this point is because from the left it has a positive rate of change, and from the right it has a negative rate of change. So if we look at this representation here of the function for the derivative of that graph I just had up there, we can see that it has a jump discontinuity at this point because it immediately jumps from a positive rate of change. As you can see, this function is positive before the jump, and then it jumps right to a negative rate of change as the function is negative. And so you can also see that there's a correlation between positivity, negativity, and the sign of the derivative. And moving on, the last reason a function may not be differentiable at a point is if it has a vertical tangent. And essentially what a vertical tangent means is that you can draw a tangent line from up to down at a certain point. And so this graph actually has a vertical tangent at this point here, because you can see that if you drew a line through this point, it would only touch one time. And the reason this is not differentiable again ties back to the idea of slope. The derivative is the slope of the curve at that one point. And given that slope is rise over run, what we actually notice here is that because this is essentially a straight up and down line that we're trying to find the derivative of, there is no run. It only goes up. So therefore, if we tried to find rise over run, we would have rise over 0, and anything over 0 does not exist. So that is why the derivative does not exist, because there is no slope at that point. And so here are what the functions for the derivatives of all these graphs would look like, and you can see that they actually have points that do not exist on all of them, which represents how they are not differentiable. So as you're learning more about derivatives, keep in mind that every function has a corresponding function that represents its derivative, and I will be explaining ways to find those functions in other videos. So thank you so much for watching, and I hope you learned something.